Hello. Thank you for having me. The title for the presentation is Potential Microbial Hydrogen Consumption During Hydrogen Storage. And this presentation is made together with my colleague Silvan Hoot and also Nicole Dopfel at NORS. Yes, as I mentioned, my name is Jannike Beda, and I'm a specialist in reservoir technology and have many years of experience with subsurface microbiology. And I'm working in Equinor. It's an energy company and has a long history of oil and gas production, but are also involved in renewables as wind and solar and also hydrogen. Yes, the objectives of this work package 8 was to determine the current microbial communication in the salt cavern and investigate any changes in microbial community during hydrogen storage and cycling. And also to investigate the scale of biological risk factors in terms of hydrogen sulfide and methane production, as well as hydrogen consumption. And also to provide information about the level of impurities to be expected under operational condition. So the main target was to investigate the difference in the microbial community before and after hydrogen injection. And this has been in close collaboration with Storengy, and this was invaluable assistance with getting the samples. So to summarize the high-level results of the work package, the cavern contains living sulfur-reducing bacteria, or SRBs as they're called, which can consume hydrogen and generate H2S. And the microbes grow slowly, and the microbes need additional nutrients to be able to grow. So hydrogen is a very good energy carrier, and it's also a preferred energy source for many microbes, both bacteria and archaea. So this shows the different opportunities regarding using hydrogen as an energy source for microbes. They can use ferric iron and reduce it to ferrous iron. And they can grow with the CO2 as a carbon source and use the hydrogen as energy source. And then they can either produce methane or acetate. And the most detrimental is when they use sulfide from the water or from the brine or from the minerals and reduce that to hydrogen sulfide. We'll come back to the risk related to the hydrogen sulfide. And some microbes can also utilize nitrate and reduce it to nitrogen gas. So these reactions are well known, but what is the scale of the problem? And the cavern is a hostile environment due to high salinity and also high pressure. But even so, some microbes are specialized in growing at high salinity. So this is not a problem for them, or it might be more slow growing, but it's nothing to, it doesn't eliminate microbial growth. Doesn't. Okay, thank you. Yeah, there are several possible consequences of subsurface microbial activities. Let's see if I can show a pointer. Yeah, they can have, as mentioned, these microbes can generate H2S. And this is both a toxic and corrosive gas, and also consumption of hydrogen causes a loss of hydrogen during storage. And also they can contaminate the stored gas and make a demand for purification afterwards. And the similar, if they're growing when the CO2 can generate methane and acetate, and that's also causing loss of hydrogen and also contamination of stored gas. This microbial activity can cause microbial influence corrosion, both directly and indirectly, and also can cause reaction with minerals, both dissolution and precipitation. And also the increased growth can cause formation of biofilm and cause fouling and plugging. Yes, this is to show the strategy for the sampling. As mentioned, we wanted to compare the microbial community before and after hydrogen storage. So this is the first sample was taken. Let me see. This is taken here before the hydrogen was injected. Actually, we took 2 samples, and then it's now this stage where the hydrogen has been injected and it will be cycling. And then after the cycling is finished in mid-March, hopefully, we will take the new sample to investigate what's happened after storage. So we have taken 2 samples, one in October 2022 and one in March 2023. And we investigate the microbial activity by DNA analysis, enrichment cultures, and chemical and physiological measurements. And with a wireline sampling in 2022, it was taking sample from 950 meters depth, and the pressure 112 bar, and the temperature was 45 degrees. So with the brine, we did the chemical analysis to investigate any potential organic carbon for growth, and also volatile fatty acids. And we investigate the pH and sulfate content, as sulfate content is critical for growing of sulfate-reducing bacteria. And the DNA analysis to determine the cell numbers of several key groups, and also to investigate the microbial community structure, and also the microbial growth and hydrogen consumption. The question, where can we detect hydrogen consumers? How will they grow? And will they produce hydrogen? So we did some chemical analysis of, and also some microbial analysis of the sample taken in 2022 and March 2023. And in general, they are quite similar, especially for the salinity and sulfate content. There's some differences regarding the pH and also the total carbonate. And a bit more microbes detected in the last sample, but in general, there were few microbes present in the 2 samples. And this is to describe the experimental setup. We had several glass bottles where we injected brine in the bottom, and then we could exchange the headspace with different kind of gas. It could be either 100% hydrogen or a mixture of hydrogen and CO2, or it could be nitrogen when we had some control experiments. And then there were added some different substrates to boost some growth. Let's see. Yeah. And then these bottles were incubated at 4 different temperatures for 1 year. And it was taken samples every 50 or 100 days. And they were taken gas samples to analyze for the gas composition and also to see any changes in the pressure. And the liquid was analyzed for pH and chemical compounds. And this shows the different combination of nutrients added, and also the gas added to the bottles, and at the 4 different temperatures. And the different colors illustrate different the different components was added. And as carbon source and nutrients, we added acetate, yeast extract, vitamins, or formiate, and with some different combination of gases. And there are several indications of microbial activity. We can investigate growth as increase in some cell numbers, and loss of hydrogen, pH increase, and hydrogen generation, and also color change. And for this, these 4 temperature incubations, at 80 degrees, we did not see any activity. That was quite expected due to the temperature of the sample. And at 60 degrees, we saw some hydrogen loss and also pH increase. And at 45 degrees, we saw hydrogen loss. And at 30 degrees sample, we saw hydrogen loss, pH increase, and high hydrogen sulfide, and also iron sulfide precipitation. So for the 30 degrees samples are not only indications of growth, we actually could demonstrate that there were microbes utilizing hydrogen, and they generated hydrogen sulfide. So this is the sample at 30 degrees with yeast extract and acetate and hydrogen. And as you can see, it took a long time before the sulfide production could be observed. It took almost half a year, and then it was suddenly 910 ppm sulfide. Well, you can see there's some days in between the sampling. And after the next sampling, it was double the sulfide measurements. And this was the first parallel, and we also had the second parallel in the pair. And that was only observed, the growth was not observed until 1 year after the start of the experiments. That is why it's very important to have this going for a long time. And we also could observe some precipitation of indicating hydrogen sulfide. And this is, okay, 1 minute. And this is the experiment with this utilization of hydrogen, see the hydrogen consumption. And for one of these cultures, it grew in 60 degrees. It could see that it can consume the hydrogen. This is the graph. And these are parallels with control. So we have to see the difference between the controls and this. And it also noticed that it was generated hydrogen sulfide. So this was evidence for the hydrogen consumption by microbes utilizing hydrogen and producing hydrogen sulfide. So the detection of hydrogen sulfide is a direct evidence of microbial hydrogen consumption, and sulfide reduction is sulfide reduction and sulfide generation, and the pH increase is indirect evidence of hydrogen consumption, and also the increased hydrogen loss rate is indirect evidence of hydrogen consumption, but it is very important to have controls present as shown in the previous slide. So the conclusion is that the brine samples were taken and microbes were detected with DNA analysis. And enrichment of 1 year showed activity of SRBs producing H2S, and additional nutrients were needed to foster microbial growth, and hydrogen loss was minimal when compared to the controls. So the carbon control contains living SRB, which can consume hydrogen, but they are nutrient limited and slow growing. So there's actually a risk of microbial hydrogen consumption and hydrogen sulfide production, but at very low rates. And therefore the microbial activity should be monitored. And it's very important to not add any chemicals that can act as nutrients, because that can increase microbial activity. So the next step is to take new samples after 100 days of cycling. And then they will do the same microbial investigations as for the first sample. And then we will see if there's a risk of increased microbial activity after hydrogen storage and potential hydrogen consumption. Because the first sample, these microbes has not been exposed to hydrogen. So for the next sample, after 100 days of exposure to hydrogen, it could be quite similar or a different picture. Yes, I also want to acknowledge my colleague Daniel Bolt, who took one of the samples. Thank you.
Thank you.